This week we are talking about minerals and rocks. Eventually we'll describe the rock cycle, but first let's start with the tiniest pieces of matter. An element is a substance that cannot be broken down into other substances by ordinary chemical methods. Gold, for example, has the element symbol Au. If you break gold into smaller pieces, you just get tinier and tinier pieces of gold. The periodic table of the elements, shown here, might be useful in this week's lab. I will remind you how to read one of these icons. An atom, if you need a reminder, is the smallest particle of an element that retains all the properties of that element. So what we are talking about today are tiny things, and we will move towards larger and larger things by combining those tiny things together. Now you might remember that an atom was made out of protons, neutrons, and electrons. If protons and neutrons are equal, it has no charge. If there are more protons than neutrons, it is positively charged. And if there are less protons than neutrons, it is negatively charged. Negatively charged atoms are attracted to positively charged atoms. Don't worry about the energy shells of an atom. You might be remembering them from your chemistry class in your past, but we will not spend time on electrons. If I look at one symbol from the periodic table of the elements, say for example I take the first element, hydrogen, the H stands for hydrogen. It is symbolic. The 1 is the atomic number. That's like hydrogen's social security number or fingerprint. It always is the same for hydrogen. If it were 2, it would not be hydrogen. And the mass is a little bit bigger than the number. It's the atomic weight. I mentioned positively and negatively charged atoms. They are called cations and anions, and they are attracted to one another. You will not need to know these terms for the lab, but I want you to think about sodium, which is positive cation, chlorine, negative anion. If I stick sodium and chlorine together, I get sodium chloride, table salt to you and me, and a sedimentary mineral. Water is a very famous molecule. 2 hydrogen atoms, 1 oxygen atom, H2O. Caffeine is probably my favorite molecule. Don't memorize it, but maybe a round of applause for caffeine. If I stick these atoms together, I get a mineral. A mineral has a very strict definition. It must be naturally occurring, it must be solid, it must be organized. The atoms have to make a very particular pattern. Here's an example of a very particular pattern used in art. M.C. Escher drew variations on mathematics, weird drawings including staircases and impossible reflections. So you can make any structure by repeating a pattern, even a piece of art. If I vary that structure at all, you get 2 different minerals altogether. You might recognize ruby. It's a type of corundum, don't worry about that. But ruby is almost chemically identical to sapphire. However, the arrangement of the same atoms change the color. Graphite here is made out of carbon. It's very soft and slippery. In fact, what you and I call pencil lead is actually graphite, slippery carbon. But diamond is also made of carbon. This is a beautiful canary yellow diamond from South Africa. You and I will never buy one of these, but maybe if you were J.Lo or Mariah Carey or somebody with a lot of money and a lot of diamonds, you would have one. It's also made out of carbon, and it's very, very strong. Soft, hard, carbon, carbon. The reason they are so different is because of the way the carbon atoms are arranged. In diamond, shown here on the left, there are many bonds between atoms, strengthening it. In graphite, shown on the right, the carbon atoms are arranged in sheets that slip past one another. Here is a list of the most common elements in Earth's crust. You don't need to memorize them, but you may refer to this slide when you work on the lab. Notice that oxygen and silica are the majority by weight. In fact, half of our crust is made out of oxygen. It is always combined with something else. On its own, oxygen is very explosive. Silicon, you may know this as glass or obsidian, is made out of silica and oxygen. By the way, obsidian is not technically a mineral because of the irregular arrangement of the silica and oxygen atoms within it. They're not regular. Technically, it's not even a solid. It's a liquid. I know, it's weird. It's a liquid that flows very slowly. Olivine is another silica and oxygen mineral that makes up the Earth's mantle. If you have an August birthday, this is your birthstone. Regular people call it peridot. Geologists call it olivine. The most common arrangement of atoms in all of these minerals is the silica tetrahedron. Tetra means four, hedron means shape. It's a fancy way of saying four-sided pyramid. There's a little silica ion, and these are oxygens. So, in summary, a mineral has to be solid, it has to form naturally, and it has to have a specific chemical composition, organized. The most common minerals, the ones we will use, are feldspar, quartz, pyroxene or pyroxene, amphibole, and mica. There are common rocks on Earth made of minerals with no oxygen and silica. Calcium carbonate makes limestone, for example, very common, and things we dig up to sell and make a lot of money from, including gold, copper, and diamond, have only one element. This is the last slide we'll talk about. The other PowerPoints refer to different rock types, but in summary, I want to show you the order in which minerals form. If I have liquid lava, just a liquid mess with no solid crystals in it yet, I can form crystals by cooling off that liquid magma, that liquid rock. The first one to form is olivine, then pyroxene, then amphibole, then biotite, so on until I get to quartz. This is the last mineral you form. Now, if I take a rock and I melt it, the first mineral to melt is quartz, followed by muscovite, orthoclase, plagioclase and biotite, amphibole, more plagioclase, pyroxene, olivine. Form, melt, cool, melt. The first minerals to form are called mafic. Mafic minerals form at divergent boundaries. A common mafic rock you have heard of is basalt. The ocean floor, for example, is made of it. Now, a divergent boundary forms these. What about a subduction zone? Subduction zones form intermediate crystals. Amphibole, biotite. A common rock made of intermediate crystals is called andesite, just like the Andes in South America, a famous mountain range formed above a subduction zone. The Andes are made of andesite, andesite. What about these crystals down here, the so-called felsic minerals? These form at convergent boundaries that are continental crust crashing into continental crust, like the Himalayas. Convergent boundaries with no subduction zone, convergent boundaries with a subduction zone, and divergent boundaries. Now proceed to the next PowerPoint to learn about the rock cycle.